I'd like to start with a bit of trivia, and we finish with a bit of trivia as usual, so at least you get something out of the lecture if you don't get anything from the middle of it. Yesterday, I gave a speech, and there were two slides which I liked from there, so I thought I'll share them with you. When there was the tussle about local time and universal time or London time, one compromise was, we probably see a lot of these compromises in lift installations. They had 2-minute handles. One that kept the local time, and one kept the London time. Because actually, we have unified time around the country, so you have local time. So that was an interesting compromise, so people could see what the local time was or what the London time was. Okay, so today I'm going to talk about double-deckers, a good introduction by Stefan, so it's quite appropriate. There's a new coefficient which we've developed called the passenger transfer efficiency coefficient in double-deckers. So we'll ask first the question, and it's an obvious question, or you might think it's actually a trivial question, but in fact it's not as trivial as we think. Why are double-deckers efficient? Any answers? Why is a double-decker good? Yes? Number of? Good, okay, stops, that's good, that's one. Again, anything else? Why do we bother? Yes?
Number of lifts, you can reduce number of shafts.
Number of shafts, and in fact, probably number of shafts is the biggest drivers we're reducing. And the third one? Yeah?
You can carry more people.
Yes, but then if you've reduced the number of single lifts, basically you've taken the car and put it on top. But yes, but there is a third one. Passenger transfer in and out. Now, that's not the strongest one, but that's the one this paper is going to talk about. I think we need to make ourselves think, why do we use double-deckers? So the PTEC, I'm going to give you 3 examples. The effect on the round-trip time, comparison to coincidental stopping coefficient, which Richard, I think, calls figure of merit. That's right, yes? So I've used it here because I had to distinguish between the two coefficients. And then we'll conclude. So the sources of efficiency is reduction in core space, and I think that's the biggest driver. And that's why, obviously, multi and so on we're trying to reduce core space. That's really the net lettable area, and that's what the developer understands. So core space. Then you have the number of stops, and I think that's the second factor. And the third one is the passenger transfer time. So the reduction in core space is obvious. Reduction in the number of stops. In fact, if we have 2 decks, we reduce the number of effective floors by 2. If you had 3 decks, which there aren't, I'm told there aren't any 3 decks, but Jim Fortune he was dreaming about a multi-deck car in one of his papers. So he would talk about a 3-deck and a 4-deck and a 5-deck car. So in theory, if you had a triple-deck car, you would reduce the number of effective floors by 3, and hence the stops. And in general, if you had a K-deck car, you reduce it by, obviously the multi has put an end to that. People would not be pursuing that direction anymore. Now that is similar to sectoring. So sectoring as well, you actually reduce the number of effective floors by S. So you divide it by S. And that's the second source of efficiency. So looking just at that equation there, you will see what we've done, we've divided N by 2. If you have S sectors, you divide N by S. If you have 3 decks, you divide N by 3. And you multiply the number of passengers by 2 or by 3. So you increase the number of passengers and reduce the number of floors, and that leads to a reduction in S. And reduction in passenger transfer time, which is really the subject of this paper. I can't go through this presentation without getting on my hobby horse. What is my hobby horse? I'm sure you will guess it. Where's Dave Cooper? Gina, what's my hobby horse? Monte Carlo simulation, excellent, thank you. So, that's the general arrangement of a double deck. And I'm going to give you 3 examples. And in fact, I actually, when I started doing this, I thought I'm going to ditch the whole presentation and just show these 3 slides. And that shows you the strength of of diagrams and figures. And if you can understand these 3 slides, you basically understood the lecture. So let's concentrate on these 3. We have a very, very tidy situation where 10 passengers get into the upper deck, 10 passengers get into the lower deck. Obviously, we have 20 in, we must have 20 out. So on every floor, we have 4, 4, 4, 4, and 4. 4 times 5, that's 20. But this is actually very, very tidy. This is, in fact, the most efficient scenario. So you have 2 getting out and at the same time 2 getting out. So we only delay the system by 2 seconds. And then 2 seconds, 2 seconds, 2 seconds. So 10 seconds. This is the most efficient. Hypothetical, it might not happen, or very, very, might not happen very regularly, but if it does happen, the PTEC is 1. So we've managed to get them in 10 seconds and get them out in 10 seconds. But that's because they were very disciplined. So they all went to the same floors. And we don't have any non-coincidental stops, by the way. Now, this is less organized. So we have 5 seconds here because we have 5 getting out and only 2. That's still a coincidental stop. Non-coincidental stop. So this is where passengers at the upper deck will be thinking, why did we stop? They stopped to get these 3 passengers out. 5 and 3, that's 8, 10, 15. So the PTEC is 1.5. So the efficiency has dropped. And then the third case is very chaotic. So we're actually at the upper limit of all of the stops are non-coincidental. We stop to get 5 here, out, 3, 2, 5, and 5. The sum of those is 20, so the PTEC is 2. So that is the least efficient situation. And basically, you can see PTEC is running from 1 to 2. So 1 is the most efficient, and 2 is the least efficient. So you can see here some numbers. So for P, passengers per deck from 10 to 20, that's the number of floors above ground and passengers per deck. And you see the number running somewhere between 1 and 2. And in most cases, it's around 1.4, 1.3. Now, an important distinction, this is for collective. What Adam called earlier collective versus destination. So this is the conventional, we're getting around 1.3. If we went to destination, it will actually go down dramatically. It will be near a 1 or very near to 1. And that can be calculated. This compares to coincidental stopping coefficient, which, as I said, Richard calls figure of merit, which is the number of coincidental stops over the total number of stops. So if we apply this to round trip time, we can do all the calculations. The formula is in the paper, more formulas. But in fact, if you use Monte Carlo simulation, it's much easier because all you do, you keep on throwing these pair of dice and you get different scenarios. You calculate it, you come up with a number. So Monte Carlo simulation would be much easier. Going back to the conventional equation, this is actually still quite a useful equation, although it only applies in cases of equal floor heights, rated speed attained in one journey. But it's always useful to go back to this equation because you can start understanding how the effect of an algorithm has on the value of the round trip time. So you can see H actually doesn't come down with double deckers, but H comes down with sectoring. The main reduction with double deckers is S, and then maybe the transfer time. If PTEC was 1, then that's just 1 plus 1, that's 2. But if PTEC is 2, then that's 2 plus 1, that's 3. S comes down because we reduce the number of stops if it's 2 decks, but you can now see the difference between that and sectoring. Sectoring will actually reduce H dramatically, the highest reversal floor. It will also reduce S. It wouldn't have an effect on PETC. So this equation is actually useful sometimes, not just for calculation, it's for understanding what is happening, understanding what's happening behind the numbers, what's happening in an algorithm. Okay, so that's the comparison with the coincidental coefficient, and I'm going to try to save you some time. I think I'm going to recover some time, Adam, for you, so you have to thank me for that when we finish. So there are 3 sources of efficiency gained from double-deck lifts. One of the ones we've discussed in this is passenger transfer time. Not necessarily the most important one. The most important benefit from double-deckers is the reduction in core space. I've called it PTEC, and I've given a name to Richard's one, which is CSC, so you have now 2 different coefficients. CSC, coincidental stopping coefficient, PTEC, passenger transfer efficiency coefficient. It ranges from 1 to 2. 1 is the best, obviously. 2 is the worst. With destination, you can probably bring it down to 1. Sorry, just above 1. You'll never get it down to 1. But with a destination group control system, you might get it to something like 1.1, 1.2. Okay, and to finish on some trivia again. We were talking about time yesterday and how humanity has come a long way in actually keeping time. So strontium clocks, atomic strontium clocks, can keep 1 second in every 15 billion years, which 15 billion years is the life of our universe. Thank you very much for your attention, and thanks, Alan.